Welcome back everyone. In this lecture we will compute graded characters of tensor product, symmetric product and exterior products. So let's actually fix some notations. So let's take V to be finite dimensional G representation. So this is finite dimensional G representation and let's fix one element G in G. So then this element G is going to act as a diagnosable operator on capital V. So maybe let's write this rho is the representation given by rho, which is acting on capital V. So we want to look at what happens to rho G. So rho G acts diagonalizably on capital V. So because it is a diagnosable action, so we can actually have eigenbases for this operator acting on capital V. So let us denote V1 etc. Vn. So this to be the eigenbasis. So this is the eigenbasis of capital V. So that means it is eigenbasis for the operator rho of G acting on capital V. So rho of G acting on capital V. So now with the eigenvalues we write it as lambda 1 etc. lambda 1 etc. lambda n. So that means rho of G on Vi is given by the equation lambda I Vi for I range from 1 to n, where n is the dimension or the degree of this representation. Okay, this is the setup we have. Now if we are taking this tensor product or the tensor algebra, so what happens? So you have this T of V, which is the direct sum of TKV, k range from 0 to infinity. So now we already seen that the character of this TKV and the character value applied on G, so is going to be just the character of the tensor product, k-fold tensor product on capital V of G. So this we already computed what it is. So this is exactly equal to, you take the character value and then raise it power k. So this is what we already had. So now if we put them together, then what we get? So you take this tensor product and then it is not difficult to see, we have this eigenbasis that is obtained from this eigenbasis of capital V. So we can take this Vi1 tensor etc. tensor Vik with the indices I1 etc. Ik comes from 1 to n, and this is indeed eigenbasis for this space TKV. So that means the action of G on TKV is diagnosable and the corresponding eigenbasis is this. And it is easy to compute the eigenvalues of G acting on this V tensor K. So what are they? They are going to be just the products lambda I1 etc. lambda Ik. So this Vi1 etc. Vik will have the eigenvalues lambda I1 etc. lambda Ik, and these are all the eigenvalues of this operator G acting on this tensor product V tensor K. Okay, so now if you are interested in computing the character value, you can see that the character value on this tensor V tensor K, so this is going to be exactly equal to sum of all this lambda I1 etc. lambda Ik, where I1 etc. Ik runs over from 1 to n. So which is exactly equal to lambda 1 plus etc. plus lambda n power k. So which is what we claimed, this is chi V of G power k. So this is what we have as the character on the tensor. So, now if we look at this generating series or the graded character, so what it is? So, it is by definition you take the sum over k range from 0 to infinity and the character of this kth graded space, which is the V tensor k of g and then t power k. So, this is what we want to compute. This is the graded character, and what it is? This is by definition. So, we already obtained as in terms of this chi v of g. So, it is just a kth power of chi v of g. So, if we substitute back there, so then we get exactly this is equal to k range from 0 to infinity chi v of g power k t power k. So, now this exactly look like a geometric series. Recall, as a formal power series, if x is the variable, then 1 divided by 1 minus x is given by summation x power k, k ranging from 0 to infinity. So, if we use this formal power series, then we can simplify this summation as the following. This is exactly equal to 1 divided by 1 minus chi v of g t. So, this is the final answer. So, when we look at this graded character, that is actually simplified in somewhat much simpler way. So, here the way we want to treat this series, so we do not talk about any convergence here. So, we are actually treating this as more of formal power series. As long as the coefficients of t power k make sense, then this series actually well defined, there is no issue. And in the formal world, we are actually talking about the taking the inverse of this 1 minus chi v of g t, and which is equal to this by definition. So, it is a somewhat another way of writing the same thing in terms of this formal series. Actually, it takes somewhat compact form when you are looking at the graded character. So, let us actually look at what happens to the symmetric power. Again, this will also have a very nice compact form. So, let us look at this sim kv. So, this is what we are interested in actually computing. So, what will be the character of this? So, we already identified this with skv, and this is true as g representations. So, if you are interested in computing the graded character of s of v, then it is enough to compute the graded character of this sim kv or skv. So, now look at what happens to the eigenvalues of the sim kv. So, we already seen that what will be the basis. So, if we take skv, so this is indeed spanned by small xi1 etc. small xik. Sorry, I have used vi. So, let us change this. So, recall that v1 etc. vn is the eigenbasis of capital V. So, with respect to the operator rho of g, okay, rho of g acting on capital V. So, now if this is indeed the eigenbasis, it is not very hard to see vi1 times etc. vik, where i1 are arranged in the increasing order from 1 to n. So, that will form a basis for this sk of v, and that is indeed eigenbasis for this sk of v, with the corresponding eigenvalue being the product lambda i1 etc. lambda ik. So, the corresponding, so this look at this g eigenvalue, and this is exactly lambda i1 etc. lambda ik. So, if we are computing the trace, we can see that the trace of this sim kv of g is exactly equal to the trace of skv of g, and which is exactly the sum of all the eigenvalues, which is lambda i1 etc. lambda ik, where i1 are arranged in the increasing order comes from 1 to n. So, this is what we have, and these functions are actually very interesting functions to study. So, they are actually symmetric polynomials, and they are called the k complete homogeneous symmetric polynomials. So, this is what defined to be h k of lambda 1 etc. lambda n, and this is, we call it as the K complete homogeneous symmetric polynomial. So, this is the definition of the K complete homogeneous symmetric polynomial, and by computing explicitly the character in terms of the given eigenbasis v 1 etc. v n of v with the eigenvalues lambda 1 etc. lambda n. So, we can see that, so the character of this symmetric power is given by this K complete homogeneous symmetric polynomial. So, let us see how one can actually simplify this further. So, if we are computing this graded character, so the graded character is given by summation k range from 0 to infinity and then chi sim k of v of g t power k. So, this is what we want to compute. So, this is by definition which is equal to summation 0 to infinity h k of lambda 1 etc. lambda n. So, that is what we get as the character of sim k f v. So, this is going to be equal to this. So, now if we think about it, this one can actually rewrite in terms of the product of 1 divided by 1 minus lambda I t. So, let us see how one can do that. So, recall that 1 divided by 1 minus x is given by 1 plus x square and so on. So, in particularly if we take 1 divided by 1 minus lambda t, so this is given by 1 plus lambda t square and so on. So, now if you look at this product 1 divided by 1 minus lambda I t where I range from 1 to n. So, this is going to be exactly equal to the product 1 plus lambda I t lambda I square t square and so on, where the product runs over from 1 to n. So, now if we look at this product, this you can rewrite as a summation. So, if you rewrite this as a summation, then what you get, you have to take all possible products among these lambda I t powers. So, if you fix t power k and then collect all possible coefficients, then you can see that. So, where k ranges from 0 to infinity, the coefficient of t power k, the contribution will come from each powers of this lambda I t. So, now you collect all possible powers and then whose exponents add up to k. So, that is going to give us t power k coefficient. So, what will be the coefficient? The coefficient is going to be, for example, from the first product we get lambda 1 power m 1 and so on. From the nth product, let us say we get lambda n power m n. So, then these exponents m 1 plus etc. m n, they should add up to k. So, this is what we should get. And if you think about it, this is another way of writing the K complete homogeneous symmetric polynomial. So, this is exactly equal to h k of lambda 1 etc. lambda n. So, if we go back to the other definition, here we are running over all integers which are increasing I 1 etc. I k, that comes from 1 to n, increasing indices I 1 etc. I k, that comes from 1 to n. So, now if you just collect those indices which are equal, then you will get certain powers of lambda I. So, you get some lambda 1 power m 1 etc. lambda n power m n, where m 1 etc. m n, they just vary, they are some non-negative integers whose add up to k. Okay. Basically, this is another way of writing same h k lambda 1 etc. lambda n. So, that tells you that this product is indeed equal to this summation. So, that actually tells you that this can be written as follows. You take the product I range from 1 to n, 1 divided by 1 minus lambda I t. So, this is what we get. So, now let us use this identity and then rewrite everything in terms of lambda i's. So, note that the lambda i's are the eigenvalues of this row of G. So, lambda 1 etc. lambda n are the eigenvalues of this row of G. So, now if you take any powers of this lambda 1 etc. lambda n for fixed power k, that will be eigenvalues of this row of G power k. So, lambda 1 power k etc. lambda n power k. So, it is going to be eigenvalues of this row of G power k, and G power k is going to be element in the group. So, it makes sense. So, now how are we going to use this in order to get the character that we are interested in? So, we will take this identity. So, this identity we will take and then use logarithm technique there. So, let us rewrite everything. So, we have this identity summation chi sim k of v of g t power k, where k range from 0 to infinity is going to be exactly equal to product 1 divided by 1 minus lambda I t, where I range from 1 to n. So, this is the identity that we have. So, now what we do, apply logarithm on both sides. So, apply log on both sides. Again, what is the meaning of applying logarithm? So, if you have a series, it is again done more formally. Let us say f is given to be a formal power series starts with 1, okay, then we can talk about log of f, or you can actually take f to be any formal power series. Let us say this is actually belongs to some formal power series in, let us say, n variable. So, then I can talk about log of 1 minus f minus. So, this is going to be, by definition, it is exactly equal to f plus f square by 2 plus etc. plus f power m divided by m plus etc. So, maybe we can just assume that so we want f to actually start with either 1 or 1 minus f to start with 1. Okay. The constant coefficient of 1 minus f, okay, constant coefficient of 1 minus f should be 1. So, that is the demand that we make. Okay. So, that is equivalent to saying that f of 0 is exactly 0. With this case, we will be able to define this logarithm formally, and we are going to use that logarithm here. So, if we take the logarithm, then what happens? So, we get log of, okay, we can put the minus here, minus log of summation chi sim k of v of g t power k, k ranging from 0 to infinity, equal to minus log of this product 1 divided by 1 minus lambda I t, I range from 1 to n. So, maybe let us take the plus log, because this will give us already minus. So, note that here when k equal to 0, what we get, when here when k equal to 0, so we are going to get chi of sim 0 v and t power 0, and that is exactly going to be actually 1, because sim 0 of v is exactly the complex. So, that character is going to be just 1, t power 0 is also just going to give us 1. So, that way this power series, you can think that it is starting with 1. Okay, so, let us look at what happens to the right hand side. So, the right hand side is given to be the log of product 1 minus lambda I t, I range from 1 to n. So, the logarithm rule applies. So, the product will become summation. So, this is going to be minus summation log of 1 minus lambda I t, I range from 1 to n. So, now I can take this minus inside. So, then this is going to be minus summation minus log of 1 minus lambda I t. So, now use this formal identity that minus log of 1 minus x is going to be x plus x square by 2 plus etcetera plus x power m by m plus etcetera. If we use that, then the right hand side becomes equal to summation I range from 1 to n, summation m range from 1 to infinity lambda I power m divided by m and then t power m. So, this is what we get it on the right hand side. So, now if we collect the coefficient of t power m, then we can see that we can run m over from 1 to infinity and interchange the summation. Then if you collect the coefficient of t power m, then you get 1 divided by m lambda 1 power m plus etcetera plus lambda n power m. So, this is what we get. And if you think about it, this is exactly the character value of g power m. Okay, this is exactly this. So, then if you do the substitution, then we can see that the right hand side is exactly equal to summation m range from 1 to infinity 1 by m the character value chi v of g power m t power m. So, this is what we get. So, now this actually tells us that the log of summation k range from 0 to infinity chi sim power k of v of g t power k is exactly equal to summation m range from 1 to infinity 1 divided by m chi v of g power m t power. So, now if you apply exponential on both sides, apply exponential on both sides. So, then we get, so we get exactly summation k range from 0 to infinity k of sim k v of g t power m equal to exponential of this summation. Summation m range from 1 to infinity 1 by m chi v of g power m t power. So, this is what we get. And if you think about it, it is very powerful identity, and this we have written actually in one go all possible character of the symmetric power sim k of v. So, one can read it out the character of this sim power k v using this right hand side. Okay. So, this indeed says that the chi of sim k v of g is indeed some combinations of chi v g powers and chi v of g powers. Okay. So, this is something we verified already for k equal to 2. So, maybe I will read it out what happens for smaller values of k. So, I will leave it as exercise. So, when k equal to 1, so we know that sim 1 is nothing but v itself. So, chi sim 1 v of g is exactly going to be chi v of g. And for k equal to 2, this is something we already verified. Chi of sim 2 v of g is given by of times chi v of g square plus chi v g square. So, this is something easy to verify, and here the new formula for k equal to 3, again this can be read off from this identity. So, if you just use the exponential definition and then read it off, collect t power 3 coefficient, then what you get? You get exactly chi of sim 3 of v of g is going to be now combinations of chi v of g power 3's. Okay. So, you get exactly 1 by 6 times chi v3 of g plus 3 times chi v of g chi v of g square plus twice chi v of g cube. So, this is what we get for power 3. Okay, I will leave it to verify. So, this is something you verify, and this can be read off from this identity. That is very simple, because we are looking at t power 3. The only way you get t power 3, you take t. So, that gives chi v g power 3, and then you take t and t square, and then you take t cube, that gives chi v g cube and as well as chi v g times chi v g square. Okay, so this actually kind of unifies everything and then gives the uniform formula. So, similar thing can be done even for the exterior product. Maybe I will leave it as exercise. So, when you compute the exterior product graded character, then what do you get? So, you get exactly summation k range from 0 to infinity, the character of the exterior products evaluated at g, and then t power k is going to be exactly equal to, again we have to use some exponential, but now instead of actually having the non-negative sum, we will have alternating sum. So, that is what happened even for the k equal to 2 case. So, similar formula we are getting it for any k. So, this is exponential summation m range from 1 to infinity minus 1 power m minus 1 chi v of g power m divided by m t power. So, this is what we get for any exterior products. So, this identity is true. So, in particularly for k equal to 3, what we have, the character of the 3 power exterior product is exactly equal to given by 1 divided by 6 chi v of g cube minus 3 times chi v of g chi v of g square plus twice chi v of g cube. So, it exactly looks like what we had for the symmetric power, but with some alternating sign. Okay, this is what we are having, but with some alternating sign. So, but the important thing to note that this symmetric power and the alternating powers, okay, so they are not going to kind of they will not be completing that tensor product. So, this direct sum usually going to be much smaller than the tensor product. So, when k is greater than or equal to 3, okay, but when k equal to 2, the sum of these two things actually exhaust the tensor product. So, you get entire space, but when k 3 and more than 3, so this is not going to actually happen. So, you have only the subspace containment, but not the equality. Okay, so let me actually define what is called this dual representation and then stop. So, the dual representation I might have already defined, maybe let us recall what it is. So, we start with V being 5-dimensional G representation. So, now we want to take this dual space, which is the home space from V to C. So, all possible C linear maps from V to C, they are called functionals, and this is what we call it as dual space. And if we have action of G on capital V, let us call that action to be rho from G to GLV. So, then we can define this dual action called rho star from again G to GLV star. So, which is defined to be, you take rho star of G to be just rho V star of G. So, this is notation, both are actually means the same thing, and you define this to be equal to, you take this rho v of g and then take adjoint of that and then take the inverse of that. Okay. So, this is how you define rho star of g, and it is not difficult to see that this star and inverse they commute. So, in particularly this rho star of g is indeed given by you take rho v of g inverse and then take star. So, this identity is indeed true. So, this is same as rho of g inverse and then taking star on top of it. Okay. So, this is something we already defined, I guess. So, this defines well defined g representation on the dual, and not only that it is easy to prove. So, what will be the character of this representation? So, the character of this representation, we call it chi v star of g, is exactly given by the trace of rho star of g, but rho star of g by definition rho v g inverse of star. So, this is exactly trace of rho v g inverse of star. So, this is the thing, but it is not difficult to verify that this is exactly given by the trace of rho of g inverse, which is exactly equal to chi v of g inverse, which is also equal to chi v of g bar. So, basically chi v star of g is exactly equal to chi v of g bar. So, this is the identity that we have, and this can be verified just by looking at the eigenvalues, because once you have this lambda 1 etc. lambda n as eigenvalues of this rho of g, then it is not hard to see that this inverse of lambda i's, they will become actually eigenvalues for the rho star g. Okay. So, maybe take this as exercise. So, if lambda 1 etc. lambda n eigenvalues of rho of g. So, then let us say v 1 etc. v n is the corresponding eigen basis of v. Then we can actually talk about the dual basis v 1 star etc. v n star. So, this is the dual basis of v star, and then this is indeed eigen basis for this operator rho star of g with corresponding eigenvalues being just the inverses lambda 1 inverse etc. lambda n inverse, and that tells you that this character is exactly equal to summation lambda I inverse I range from 1 to n. So, which is exactly the character of chi v of g inverse, and since everything is unitary, so this is same as chi v of g bar. Okay. So, that is how we are getting this identity. Okay. So, I will stop here with this identity. So, maybe in the next class we will see that how to prove this orthogonality of characters again using these tensor products and dual representations.